We're going to be looking at sequences and series, which is quite a big departure from the integration techniques that we just got finished with. So when we talk about sequences and series, we want to just talk about an overview first of what those terms mean and what some of the problems will be looking like. Eventually, what we want to know is if a sequence or series converges or diverges, and then what that converges or diverges to. So let's go ahead and start talking about a sequence. So a sequence is usually a function that's defined over integers such n equals 0, 1, 2, 3, and then what we do is we plug in those values of 0, 1, 2, 3, and it produces a sequence of numbers. For instance, the sequence of odd numbers. We could look at 1, 3, 5, 7, 9, and of course that continues on forever in that particular pattern. We could also look at an alternating sequence. So an alternating sequence could be something like -2, 4, -8, 12, something like that, where every other term goes positive, negative, positive, negative. We could look at sequences that are fractions. We could look at 1/2, 1/3, 1/4, 1/5. We could continue on that one. And so we can see that this first one is getting larger and larger. The terms get larger and larger. So we would call this the terms of the sequence diverge. This one, it's not clear what's going on because I'm bouncing back and forth between a positive and a negative value. So it's not really going toward convergence or divergence. Divergent means that it's going toward infinity. Now these terms, 1/2, 1/3, 1/4, 1/5, they're getting smaller and smaller, so they're converging. And it looks like they're getting smaller and smaller and converging towards 0. They don't always have to go towards 0. It could converge to a number or a fraction as well. So to get started working with these problems, let's go ahead and just start looking at some sequences and writing out the terms. Now for this problem, it says suppose a sequence, and this is pretty common notation for a sequence. This is a curly brace. It might be kind of hard to see, which represents a sequence around the a sub n. And it's defined by the formula a sub n equals 1 over n plus 10. Now a sub n means which term it is, so it's the 0th term, the first term, the second term, etc. So this n goes back here to the value that we're plugging in. So what we would do then, if we want to find the first 4 terms, we actually start with 0. So don't think the first term starts with a sub 1 because this is defined to start with 0. So for a sub 0, what we would do is we would plug in 0 then for any n that you see in this expression. So that would be 1/10. A sub 1 would be 1 over 1 plus 10, which would be 1/11. A sub 2 would be 1 over 2 plus 10, which is 1/12. And a sub 3 is 1 over 3 plus 10, which is 1/13. So the terms of the sequence are listed here. Now usually we would list them, my math lab usually has a box for you to put each one in, but when we're working with these, eventually what we're going to do is we're going to list them in order so we can start to kind of see a pattern. Now these terms, the numerator is fixed and the denominator is increasing without bound. So eventually this is going to go towards 0. So if I look at, let's say, the millionth term, it would be 1 over 1,000,010. And so the terms are going closer and closer to 0 here. So this is an example of finding the first 4 terms of a sequence. Let's look at a few more examples. We'll look at some different types of sequences. Let's look at one that is recursive. Now a recursive or a recurrence relation that you can see right here is noted. That basically means I'm depending on a previous term in the sequence to define the next term in the sequence. So let's look to see what we have here. It says it's defined by this recurrent relationship. So we can tell it's recurrent by a couple of things. First of all, a sub n plus 1, that means our next term. And that's equal to 2 times n times a sub n. Now a sub n means my current term. So this one is not defined for starting at 0, 1, 2, 3. This starts at 1. So that's kind of what we want to keep track of here. Now I couldn't get started on this unless I was given this kind of seed value, because the only way I could get a sub 1 out of this is if n was equal to 0 and I don't have an n equals 0 term to start with. So we already know our first term is a sub 1 equals 2. Now we want to find the first 5 terms of the sequence. So let's go ahead and look at a sub 2. Well, that's a sub 1 plus 1. So remember what we're looking at here, n would equal 1. So for this case, n would equal 1 to get started. Now what I can do here then is I can plug into my formula. So that would be 2 times 1 times a sub 1. So that would be 2 times 1, and then a sub 1 was given up above. That's the recurrence part, is 2. 2 times 1 times 2 is 4. So what we would get here then is a sub 2 equals 4. So this would imply a sub 2 equals 4. Now we're going to use that information as we go to our next one, n equal 2. So for n equal 2, I would have here that a sub 3, because I have a sub 2 plus 1, is equal to 2 times n right here, which in this case is 2, times a sub 2. Now I know that we're going to have a sub 2 here because n is given right here, and n equals 2 for this case. So I just plug everything in. A sub 2 was 4 up in my previous step. That's the recursive part. So I have 2 times 2 is 4, 4 times 4 is 16. So I have a sub 3 equals 16. Now remember, I'm looking for the first 5 terms. I was given the first term, and I found the second and the third, so let's go ahead and go for the fourth. Now for the fourth term, n would equal 3, because a is 3 plus 1 is my subscript. So I'd have 2 times n, and again that's given right up here. So 2 times 3, a sub 3. Now a sub 3 I just found up above. A sub 3 is 16. So I have 2 times 3 is 6. 16 times 6 is 96. So that would mean a sub 4 is equal to a 96. Now you might look at this and see a pattern, 2, 4, 16. You think, okay, well 2 squared is 4, 4 squared is 16, so the next one should be 16 squared, which would be 256, but it's not, it's 96, so that pattern doesn't hold. So even though you think you might see a pattern, make sure you carry it out many, many different terms in the future here to see if it actually holds. Let's go ahead and look for a sub 5. That would mean n is equal to 4 in this case. So that would be a sub 4 plus 1, so n equal 4 again. So this is 2 times 4, a sub 4. Now look at all the patterns that are going on right here. So let's go ahead and look at looking down this column. Right here, I see a lot of patterns. I see 2, 3, 4, 1, 2, 3, and then I have 1, 2, 3, 4, a sub 1, 2, 3, 4. So as you're working with these, look for those types of patterns, and then you might be able to find any mistakes if you have any. So for instance, for this example, the 2's are fixed because that comes from my formula here. N is the sequential term, so that's 1, 2, 3, 4. And then these would be the previous terms, so 2, 4, 16, and 96. So for here, I'd have 2 times 4 is 8, and 8 times 96 is 768. So what I have here then is a sub 5 is equal to 768. Now we can also keep going with these terms, but we are only asked to find the first 5. Now in my math lab, you usually just fill these into the box. They'll give you a box for each term, and then you'll be asked to simplify your answer. So if it's a fraction, you would make sure it's reduced. You always put things in as exact, meaning radicals, fractions, that type of thing. You don't put in decimals unless they ask for rounding. So for the terms of this sequence, what I have here then is I start with 2, 4, 16, 96, 768, and of course this would continue on in the same pattern. And the pattern that it's continuing on in is 2n a sub n. So 2 times my current term times a sub n is my previous term for the n plus 1. So this one, the terms are definitely getting bigger, so I could think about these terms as diverging. Now this problem, they're nice enough that they give us the terms and we're just asked to try and figure out what's going on with the terms, what is that pattern? So for this one, they give us the first 10 terms of the sequence. So the first 10 terms of the sequence, this is the sequence producing function right here. 1 plus 1 over 10, and then that quantity is raised to the 10 to the nth. And then this n equal 1 to infinity, that means I start with 1, and then I go all the way up to infinity, of course, which is impossible. But what we'll do is we'll see a pattern, and we can start to predict what that term is as we're going toward infinity. Well, this is the table of values. So if I plug in n equal 1, I get 2.593, etc., n equal 2, and I can see that this pattern, I have 2.7, 2.718, and because we've worked with natural numbers a lot, that we can see that this limit then, as n approaches infinity, meaning we're trying to find what the nth term looks like, so the limit as n approaches infinity here, of the sequence, 1 plus 1 over 10 to the nth, 10 to the nth, n equal 1 to infinity, looks like to me it's getting closer and closer to 2.71828,205. It's kind of balancing out there, which is the natural number e. Okay, so here we're not looking for a decimal, we're looking for an exact answer because that's getting closer and closer to the natural number e. Now this next problem that we're going to look at is a little bit different. We're going to use the terms of the sequence, but we're going to use them to find something called a partial sum. We want the first 4 terms of the sequence of partial sums. So this is a little bit confusing because we're going to use the terms of the sequence and then we're going to add them together to find the partial sums. We can't find the total sum right now, but we can find the partial sums. So first of all, let's go ahead and write out a few terms of this sequence. So here's my sequence right here, 1 over k plus 1, and k is going to start with 1. So let's start with k equal 1. Then my term, a sub k, would be a sub 1, and that would equal 1 over 1 plus 1, which is 1/2. Then I'd have k equal 2, so that would be a sub 2. That's 1 over 2 plus 1, which is 1/3. K equal 3 is a sub 3, is 1 over 3 plus 1, which is 1/4. K equal 4 is a sub 4, and you can see the pattern here already. 1 over 4 plus 1 is 1/5. Now we're only going up to the first 4 terms of the partial sum, so I think we have enough here to finish the problem, but we can always go back and create some more if we don't. Now what is a partial sum? Well, we're going to use a notation S sub n to represent the nth partial sum, and we want the first 4 partial sums. So I'm going to look at S sub 1. And S sub 1 is just a sub 1. In this case, that would be 1/2. So S sub 2 would be the sum of a sub 1 plus a sub 2, which is 1/2 plus 1/3. And then I'll go back and I'll actually calculate these out. I just want to write these out so you see the pattern. The S partial sum, S stands for sum, is a sub 1 plus a sub 2 plus a sub 3. So that would be 1/2 plus 1/3 plus 1/4. S sub 4 is a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So again, 1/2 plus 1/3 plus 1/4 plus 1/5. Now, before we go and calculate these, I want you to notice something. We're not asked to find the 5th partial sum, but I want to show you what the pattern is here. If I were asked to find the 5th partial sum, it's just the previous one, which would be S sub 4, plus the 5th value, which would be a sub 5. So S stands for sum, A is the term of the sequence, so I could just take the previous partial sum and add the next term. So let's go ahead and add these up real quick. Of course, S sub 1 I'm already given here as 1/2. S sub 2 here, I'd have to find a common denominator of 6, so I'd have 3 plus 2, which is 5 over 6. And then S sub 3 then, what I could take is 5/6 plus 1/4, or I could find a common denominator of all 3 of these terms, which would be 12. So it would be 6 plus 4 plus 3, which would be 13 over 12. Now this I already know is 13 over 12, so I could just take 13 over 12 plus 1/5. It might be a little bit easier. My common denominator would be 60, so I'd have 65 plus 12 would be 77 over 60. So that would tell me then that S sub 4 is 77 over 60. Now this term then, I could just take that 77 over 60 and add in A sub 5, which would be 1/6. So this would be 77 plus 10 all over 60 would be 87 over 60. So you can kind of get an idea then, this is the sequence of partial sums. So then I could look at this sequence as 1/2, 5/6, 13/12, 77 over 60, and we're only asked to find the first 4, but this sequence would continue on indefinitely, of course. So what we can do from here then is we can start talking about predicting what these values are doing. So 2, 6, 12, could I figure out a way to write this function that would produce this particular sequence? So that's our overall goal, is to start developing things toward that end. So when you're working problems from here on out in this particular unit, make sure you're looking at, are you looking for partial sums? Or are you just looking for terms of the sequence? Because it's a very different problem. And in this one, of course, you were looking at partial sums. So this one, it says, write the first 4 terms of the sequence. So we're not finding partial sums here, we're just finding those terms. So this notation just means this is A sub n that produces the sequence. It's a function that produces the sequence. And this says I start at n equal 1 and I go toward infinity. And then down here they give us what A sub n is. So what we would do is we would start with n equal 1 to find my first 4 terms of the sequence. Now we're not finding partial sums on this one, so just make sure you're kind of keeping a close eye on what you're being asked in the problem. So for n equal 1, that would equal 2 to the n plus 1, but n is 1, so I have 1 plus 1 all over 3 to the n, but n is 1 in this case minus 8. Okay, so that is n equal 1. I'm going to go ahead before I calculate these, and I'm just going to fill them all out. So this would be 2 to the 2 plus 1 all over 3 to the 2 minus 8. Notice my pattern here, it's the exponent that's changing. Everything else is staying the same. Sometimes these can get a little bit confusing about what changes and what stays the same. Let's do n equal 3. And again, we're doing the first 4 terms of the sequence. So this would be 2 to the 3 plus 1 all over 3 to the 3rd minus 8. Fourth term, 2 to the 4 plus 1 all over 3 to the 4th minus 8. Now notice in the exponent, the plus 1 is in the exponent. Down here, the minus 8 is not in the exponent, so make sure you're clear about how you're writing that out. So let's go to our first term of the sequence and see what we have here. We have 1 plus 1 is 2, so I have 2 to the 2nd over 3 minus 8. This one's going to be interesting. So 2 to the 2nd is 4, and then 3 minus 8 is negative 5, so this would be a negative 4/5. So this would tell me that A sub 1 is negative 4/5. Okay, next, 2 to the 2 plus 1 is 3. 3 squared is 9 minus 8. Well, 2 cubed is 8. 9 minus 8 is 1. 8 divided by 1 is 8. So A sub 2 is equal to 8. Okay, as we continue to work here, we have 2 to the 3 plus 1. 3 plus 1 is 4. 3 cubed is 27 minus 8. 2 to the 4th is 16. And 27 minus 8 is 19. So this tells me that my third term in my sequence is 16 over 19. Okay, as we do our last one that we're asked to look at here, 2 to the 4 plus 1. 4 plus 1 is 5. 3 to the 4th is 81 minus 8. So for this example, 2 to the 5th is 32. and 81 minus 8 is 73. So this tells me that a sub 4 is 32 over 73. So if we wanted to talk about what this sequence looks like, then I'm going to pop right back up here. The terms of my sequence would be -4/5, 8, 16 over 19, and 32 over 73. Of course, the same pattern would continue. Now, I have a negative value here, and a lot of times what will happen is your terms of your sequence will alternate, meaning every other one is negative or every other one is positive. But for this one, it was just the first term that's negative, and that's fine. It doesn't always have to follow an alternating pattern like that. So again, we're just looking at the terms of the sequence, not a partial sum here. For our next example, we're going to be finding again the first 4 terms of the sequence. So we're not looking at partial sums, we're just looking at 4 terms. But this one is interesting because the sequence producing function, it starts with n equal 1, but it's a trig function. Now don't forget the 7 minus in front here. So let's go ahead and start with a sub 1. That would be 7 minus cosine of pi times 1 over 2. Now we'll evaluate these after I go through and look at all of the patterns here. So this would be 7 minus cosine of pi times 2 over 2. Okay, next one would be a sub 3, which would be 7 minus cosine of pi times 3 over 2. Notice we're getting all quadrantial angles here. A sub 4 is equal to 7 minus cosine of pi times 4 all over 2. So you can see the sequence here. Everything is staying the same because I only have one value of n, but I have 1, 2, 3, 4 that's changing in the numerator. So let's go ahead and look at our first one. So this would be 7 minus the cosine of pi over 2. Well, the cosine of pi over 2 is equal to 0. So when I simplify this, I get 7 minus 0, which is 7. So a sub 1 equals 7 here. Okay, our next term, this would be 7 minus cosine. Now here the 2's cancel and I'm left with the cosine of pi. And the cosine of pi is -1, so I have 7 minus a -1, which is the same as 7 plus 1. So a sub 2 would equal 7 plus 1 is 8. Now here, cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0. So I get 7 minus 0 is 7. So I get a sub 3 equals 7. So again, we're getting all these quadrantial angles, so I would suspect this pattern is going to hold if we kept repeating this, let's say the first 10 or 12 terms. So here I'd have 7 minus cosine. 4 divided by 2 is 2, so I'm left with 2 pi here. The cosine of 2 pi is 1, 7 minus 1 is 6, so a sub 4 would equal 6. Now we could keep going with this pattern, but we're only asked to find the first 4 terms. So my sequence so far looks like 7, 8, 7, 6, and then the pattern would continue. But those are my first 4 terms. So we can throw trig functions in here as well, and of course anything with a trig function is always more fun. Now this next one is interesting. We're doing a recursive relationship again, and we're looking at the first 4 terms of the sequence. Now the first term they have to give us, a sub 1 equals 0, so that one was kind of the easy part here. And then we have to go to a sub 2. Well, a sub 2, I'm going to start here, and that would be a sub 1 plus 1, which would be a squared n is 1, plus 4. So got to be careful here. So this is when n equal 1. So I know n has to equal 1 because I have to get a subscript of 2. What would I add to 1 to get 2? And that would be this value here, n equal 1. And of course, if n is 1, then I go to the previous term to find my a sub n squared, and then don't forget the plus 4. Okay, so if we write this out, a sub 1 was 0, so I get 0 squared plus 4 is 4. My next term, we'd look at n equal 2, which would be a sub 3, because I have a sub 2 plus 1, which would be a sub 2 squared plus 4. So the recursive part is to find a sub 3, I have to go back to a sub 2. So a sub 2 was 4, so that would be 4 squared plus 4, sorry, 4 squared plus 4. 4 squared is 16, 16 plus 4 is 20. So I should write that out. A sub 3 equals 20. Up here, a sub 2 would equal 4, and then of course my original a sub 1 was equal to 0. It's kind of the seed value that they give us that we have to start with. And we want the first 4 terms of the sequence, so we'd go up to n equal 3, and I get a sub 4 is equal to a sub 3 plus 1. The 3 plus 1 is in the subscript, which is equal to a sub 3 squared plus 4. A sub 3 was 20, so this would be 20 squared plus 4. 20 squared is 400. 400 plus 4 is 404. So this would mean that a sub 4 is equal to 404. So from here, what we have is our terms of our sequence. We'd go a sub n would equal 0, 4, 20, 404, and of course this would continue. So it's really important that you look for the patterns here. And so some of the patterns that you might see is the subscript 1, 2, 3, 4. That's based on n equal 1, 2, 3. You can see the subscript first term here increases 1, 2, 3. We can also see the subscript here 1, 2, 3, and then 4 stays constant. So it's just this pattern of plugging in and following through. Now a lot of times a pitfall to watch out for is a lot of people forget the plus 4 part. They're just so focused on the recursive part they forget the rest of the terms. So again, we're looking for patterns here. Now with this problem, things are a little more complicated. They don't give us the sequence producing function. They give us the terms of the sequence and then ask to work backward. So here we have, I'm going to rewrite this a little bit. 1 over 1, 1 over 3, 1 over 9, 1 over 27, 1 over 81, and hopefully you see the pattern here. And it says find the next 2 terms of the sequence. Well, if we want to find the next 2 terms of the sequence, let me erase the dot 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 here, we need to figure out what the pattern is. So that this would be the next 2 terms. Okay, so I can see that the numerator is staying constant as a 1 for all of these, so I can fill that in. Well, let's look at these powers. This is 3 to the 0, 3 to the first, 3 squared, 3 cubed is 27, 3 to the 4th is 81. So this must be 3 to the 5th and then 3 to the 6th. So 3 to the 5th is 243. So the next term is 1 over 243. And then 3 to the 6th is 729. So the term after that is 1 over 729. So what's happening here then is I can see that my function, the numerator is staying fixed, and then the denominator is increasing by powers of 3. So this would be part A right here, find the next 2 terms. Now next part B. Part B says find a recurrence relation that generates the sequence. That's kind of tricky. So the recurrence relationship, we already know from the previous problems, it's going to start off with a sub n plus 1 is equal to something to do with a sub n here. Now it looks like to me, if I took the previous term and multiplied it by 1/3, I would get the next term. So if I looked at this as 1/3 a sub n, this would work. And this would work if a sub 1 started out to be 1. And then this would be for n equal 1, 2, 3, etc. So you just have to kind of look at the pattern and you have to try and predict what's going on. And then you should probably plug in a few values to check. So our a sub n plus 1, our first term should be 1, which it is up here, so that worked out great. And then my next term, I should see if that works as well. So again, I'm just checking to see if this works. So a sub 1 is given, it starts out as 1, that's what I figured out here. A sub 2 should equal 1/3 times a sub 1. That's from this function right here. Well, a sub 1 was 1, so that would be 1/3 times 1, which is 1/3. And I come up here and that checks as well. So my first term worked and the second term. Let's look at a sub 3. That should be 1/3 a sub 2. A sub 2 I just found to be 1/3. 1/3 times 1/3 is 1/9, and that checks off the third term. Now, I better check just a few more. I don't want to get in the habit of just assuming, oh, if the first 2 or 3 works, they all work. We saw that in a previous problem that wasn't true. So this would be 1/3 a sub 3. A sub 3 was 1/9. 1/9 times 3 is 27. That works as well. A sub 5 is 1/3 a sub 4. A sub 4 I just found out is 1/27. 27 times 3 is 1/81. So that worked as well. So I could go forward and keep checking, but it's always good when you write one of these function that's supposed to define a sequence that you plug in values to double check that it works. Now part C, it says find an explicit formula for the general nth term. So part C is to find a formula for the general nth term of the sequence. Now explicit means it doesn't involve a recurrence. It doesn't rely on a previous term. So could I write a function here? And I think I could, because I know that 1 is fixed and then the denominator is just a power of 3. So the question is, maybe it's just 3 to the n. Well, we have to define where n starts, and in my math lab they usually tell you where they want n to start, whether they want it to start at 0 or 1. So if we wrote this out, if n was 1, a sub 1 would equal 1/3 to the first, which is 1/3. But that's not right. This does not work because my first term should be a 1, so that didn't work. But I got to start at 1. So what I want here is 3 to the 0 power. So I better take my term number minus 1. So let's do a minus 1 in the exponent here. Now let's try n equal 1. So a sub 1 would equal 1/3 to the 1 minus 1. 1 minus 1 is 0, 3 to the 0 is 1, and that checks. Okay, let me just try a couple more. Let's try n equal 2. This would mean a sub 2 is equal to 1/3 to the 2 minus 1. 2 minus 1 is 1, 3 to the first is 1/3, so that checks. So I could try the same for n equal 3, 4, and 5 just to double check. But again, I always encourage you to check several terms here. So now we're getting into the ones that are a little bit more complicated where I work backward with these types of problems. This problem has an alternating component involved. If you notice, every other term goes positive, negative, positive, negative. So this is an alternating sequence. It has to have that positive, negative, or negative, positive all back and forth. It can't just be that one term is negative. It has to have that alternating. So we have several terms of this sequence that's given. It says find the next 2 terms. So let's go ahead and write this out and see what we can come up with. Definitely I see powers of 3 here. So for part A, I have 1, -3, 9, -27, 81, and then I need 2 more terms. Okay, well, I see powers here, so I have 3 to the 0, 3 to the first, 3 squared, 3 cubed, 3 to the fourth, 3 to the fifth, and 3 to the sixth. Now I have to figure out this alternating part. So here this is negative, negative, negative. So every other one is negative. It looks like to me anything with the odd power is negative. So that's interesting to kind of keep track of. So -3 to the fifth would be a -243. And 3 to the sixth is 729. So this should kind of look a little bit familiar from our previous problems with powers of 3. So that's A. Let's go ahead and look at part B. It says find a recurrence relationship. That means the previous term has to be involved in calculating the current term. So for here, I'd have a sub n plus 1 is equal to something to do with a sub n. Well, it looks like to me that it's multiplied by 3 for sure, and then to make that alternating part, I would just multiply it by a negative, because what would happen is if my previous term was negative and I multiplied the next term by a negative, it would become positive. So that's the alternating component. Now this is only going to hold true if my first term, a sub 1, was equal to 1. And this is for n equal 1, 2, 3, etc. So integer values there. And again, we should check this. Okay, so a sub 1 was given as a 1. Let's look at a sub 2. That would be negative 3 times a sub 1, the current term, which would be negative 3 times 1, which is negative 3. So that checks as well. So I have 1, negative 3. Let's try a few more. Let's try a sub 3 is a negative 3 times a sub 2. A sub 2 in this particular case was negative 3. Negative 3 times negative 3 is 9, so that's up here. A sub 4 is negative 3 times a sub 3. So it's negative 3 times 9, which is negative 27, which works up here. Okay, so those work it out. So again, you got to check quite a few. Don't just rely on the first one or two terms. So now part C says find an explicit formula. So that means we're not relying on recurrence to find the nth term of the sequence. Well, this one's really interesting. We already kind of have an idea of what's going on here. We already said it looks like anything with these odd powers is negative. Okay, well that's interesting. And then everything with even powers is positive. So I already know that if I take a negative to an even power, I'll always get positive, and if I take a negative to an odd power, I'll always get a negative. So that's this negative 3 in parentheses. If this negative wasn't in the parentheses with the 3, then this problem would work differently. So you have to make sure that you keep track of having your parentheses in the right place. Now, what about my terms? Well, my first term has to be 1. So the only way this is going to be equal to 1 is if I plug in an n equal 1 and I subtract 1. So this is for n greater than or equal to 1 or n equal 1, 2, 3, etc. So if I plug in a 1, 1 minus 1 is 0, negative 3 quantity to the 0 is 1. So let's go ahead and check a few terms here. So a sub 1 is equal to a negative 3 to the 1 minus 1. This would equal negative 1. Because 1 minus 1 is 0, and I only have the 3 raised to the 0. The negative's not raised to the 0 because I don't have parentheses, so this is a mistake. I have to have this in parentheses in order for this to work. Negative 3 quantity to the 0 is equal to 1. So a sub 2 would be negative 3 to the 2 minus 1, which would be negative 3 in parentheses to the first, which is minus 3. So that's working. A sub 3 would be negative 3 in parentheses to the 3 minus 1, negative 3 quantity in parentheses, 3 minus 1 is 2, negative 3 times negative 3 is 9. Let's do one more. So negative 3 to the 4 minus 1, 4 minus 1 is 3, negative 27. So a thing to remember here, negative 3 squared does not equal negative 3 quantity squared. So be careful, make sure that you're using those parentheses. Negative 3 squared is negative 9, negative 3 quantity squared is equal to a positive 9. So be really careful about including the parentheses in the right spots. Now when we're working with these types of problems, noticing that they're alternating is always going to bring up this idea of a negative, positive. So there's going to be a negative involved to a power, but this one's interesting because the positive negative is alternating, but the terms are not changing. So we're going to do parts A through C. Well, parts A are to find the next two terms. So we have 5, negative 5, 5, negative 5, and then 5, and we want the next two terms. Okay, so we have here and here are our next two terms. Well, obviously, it's going to be a negative 5 and then a 5 for the next two terms. Now, part B is that idea of using a recurrence relationship, so a recursive formula that helps us to define this. Well, I think if we look at this in terms of a sub n plus 1, I just look at the previous term, which was a sub n, and then I negate it. And this is going to be true if a sub 1 equals 5, and our values for n start with 1, 2, 3, etc., which is n greater than or equal to 1. So we want to check a few of these. So a sub 1 is given as 5. A sub 2 would equal negative a sub 1. So that would be a negative 5. And so that checks. So that's 5, negative 5. So let's do a sub 3. That would be a negative a sub 2. A sub 2 is negative 5. Negative times a negative is a positive 5. A sub 4 would be a negative a sub 3. A sub 3 was a 5 minus 5. That checks as well. So we can see that we're off to the races there, and that's correct. Now C would like us to find an explicit formula, meaning I don't rely on the recursion. Well, I think this one will actually be pretty easy. I need to get things to alternate here, and I need them to start with, if I'm going to start with n equal 1, n equal 2 goes here, n equal 3, n equal 4, n equal 5. So it looks like to me the evens are negative this time. So that's a little bit different, because the last problem we worked at was the odds that were negative, and that's easy because I know anything that's raised to an odd power will end up being negative if the base is negative. So this one's going to be a little different. I can think of a couple ways that we might want to rewrite this. So a sub n for the explicit form, I could have negative 5. Sometimes some of these are trial and error, so let's see what we can get to work here. Remember, this is n equal 1. So a sub 1 here. I want to get a positive 5 out of this, so I would have to raise that to, this is really complicated because as n increases, n equal 2, n equal 3, etc., my power can't increase. Because if my power increases, then I'll get 5 squared, 5 cubed, 5 to the 4th. So I'm going to rethink this. I don't think this will work. I can't raise the 5 to a power. I can only raise the negative to a power. So this would be 5 times a negative 1 to the, let's try n minus 1. Let's see if this will work. And if it doesn't work, it's trial and error. We'll try something different. So if we plug in n equal 1, I'd have 5 to the negative 1 times 1 minus 1 is 0. Negative 1 to the 0 power is 1. 5 times 1 is 5. So that works up here. So that could work. Let's see what happens here. A sub 2. This would be 5 to the negative 1 times 2 minus 1. So it would be 5 to the negative 1. 2 minus 1 is 1. 5 times a negative 1 is a negative 5. So that works. Let's try again. A sub 3 is 5 times a negative 1 to the 3 minus 1, which is 5 to the negative 1. 3 minus 1 is 2. Negative 1 times negative 1, so negative 1 quantity squared is 1. 5 times 1 is 5. So that's working. So that would be one example. So one example of our explicit would be this piece right here. Okay, now I think we could rewrite this another way too. I think that we could rewrite this as 5 to the negative 1 times the n plus 1. And we're going to get the same thing, because when I plug in 1, 1 plus 1 is 2. Negative 1 quantity squared is a positive 1. 1 times 5 is 5, and that gives us our starting point right here. Now if we plug a 2 in here, 2 plus 1 is 3. Negative 1 raised to the third power is going to be a negative. 5 times negative 1 is negative 5. Okay, so this would be another way to write that. So sometimes there's more than one way that we can write these out. The important thing is you always check them. Well, for this problem, we're given the sequence producing function, and we're asked to find the first 4 terms, and we're trying to decide if the terms of the sequence appears to converge or diverge. Okay, so we have to have an explanation there. Well, let's go ahead and start by working out the first 4 terms. So a sub 1 is going to be equal to n equal 1, because they're telling us our start value is n equal 1. Okay, so for n equal 1, that would be a sub 1, which would be 4 to the 1 minus 5. I'm going to go ahead and just write all of these out, and then I'll calculate them. A sub 2 is equal to 4 to the 2 minus 5. And the reason I do this sometimes is so I can see the pattern and I don't mess up the pattern by switching the 4 to a 3 or something like that. So notice it's only the exponents that are changing here. 4 to the 4 minus 5. Okay, so let's start at the top. 4 to the 1 is 4. 4 minus 5 is negative 1. So this would tell me that a sub 1 is equal to a negative 1. 4 squared is 16. 16 minus 5 is 11. A sub 2 is equal to 11. Okay, 4 cubed is 64. 64 minus 5 would be 59. So a sub 3 would equal 59. Okay, our last one, because again we're going through a sub 4 here, would be 4 to the 4th, which would be 256, minus 5, which would be 251. So a sub 4 would equal 251. Now the question is, does this look like it converges or diverges? Well, if we're looking at this, these are getting larger and larger, so they're increasing and they're not leveling out. So sometimes a function will increase, but it's kind of leveling out and getting closer to a finite value. But these are not leveling out toward anything. These are increasing toward infinity. So for here, I would say that these converge. Or sorry, diverge. She said they're going toward infinity, so they're diverging. So increasing toward infinity would be diverge. So we can look at those terms, and just because they're getting larger, it doesn't mean it diverges. They diverge because the terms don't approach a single value. So these are not approaching a 1 or approaching a 10 or 100. They're approaching infinity. Let's do the same for this one. Let's go ahead and find the first 4 terms and then see if we can make some sort of a conjecture about whether it converges or diverges. So again, the first step is to find the first 4 terms in this particular case. So a sub 1 would equal 1 over 5 to the first. And again, I'm going to do all of these written out and then I'll go back and calculate them. I do that because a lot of times I'll start getting confused about what's changing and what's staying constant. But if I write them all out first, then I don't mess that up. So a sub 4 will be 1 over 5 to the 4th. So starting at the top, 5 to the first is 5, so I'd have 1 over 5. A sub 1 is equal to 1/5. Next term, 5 squared is 25. That's in the denominator, so I have 1 over 25. So a sub 2 is equal to 1 over 25. 5 cubed is 125 in the denominator, so I have 1 over 125. A sub 3 is equal to 1 over 125. And then the last one that we're finding, of course this could go on forever, 5 to the 4th would be 625 in the denominator. So a sub 4 would be 1 over 625. So these are also going toward something. The numerator is fixed. The denominator is increasing without bound. So I feel like this is going toward 0. So going toward is another way of saying converges. So what if I wanted to look at this in terms of a limit as n approaches infinity of 1 over 5 to the n would equal 0 as well. So this limit notation you're familiar with from Calc 1, and you'd also realize that this goes toward infinity because I have a fixed numerator and I have a denominator increasing without bound. So it looks like it appears to converge, and the limit kind of shows that it converges towards 0. So we've had one diverge and we've had one converge. So this one has quite a few different things about it, so we have to read this one carefully. With the terms here, it says for the following infinite series. So we're not looking at a sequence, we're looking at a series. And so the series is the sequence of partial sums. So partial sums are involved in here. So this is when we use S. S sub 1 would be the first term, S sub 2 would be the sum of the first and second terms. It says, so for the following infinite series, so I'm taking all the terms and I'm adding them together infinitely. And you would think if I added to something infinitely, meaning I kept adding and adding and adding, it would eventually go toward infinity, but that's not actually the case sometimes. So this might be a pretty interesting problem. Then it says make a conjecture about the value of the infinite series or state that the series diverges. So first of all, let's go ahead and find the first four partial sums. So S sub 1 would equal 0.3. That's this first term. S sub 2 would equal S sub 1 plus S sub 2, or sorry, A sub 1 plus A sub 2. So this is A1 plus A2 plus A3. So that would be 0.3 plus 0.03, which is 0.33. So this would mean S sub 2 equals 0.33. So let's go ahead and look at S sub 3. That would be A1 plus A2 plus A3, 0.3, 0.03, 0.03, and that comes from right up here. So S sub 3 would equal 0.333. I think you kind of see the pattern here. Now S sub 4, I don't have a fourth term here, but notice my 0 in front of my 3 increases by 1 each time. So my next term would be 0.003. So A1 plus A2 plus A3 plus A4, 0.3, 0.3, 0.003, 0.003 would equal S sub 4 is 0.3333. So those are my first four partial sums. Well, I think if I keep going here, what's going to happen is the 3 is just going to keep repeating itself, and that would be the decimal approximation for the fraction of 1/3. So the value of this infinite series, meaning if I kept adding these on together forever, would be 1/3. So this is approaching 1/3. It's not going to be exact because exactly 1/3 is 1/3, but 0.3 forever is getting pretty darn close to that decimal approximation. Now it would diverge if it wasn't going toward a particular value. So this is converging toward 1/3. Now the terms of the sequence aren't going toward 1/3. The partial sums are going through 1/3. So that's kind of what the important thing is to look at here. So this one, again, we need to be careful how we start this. We want to know if we're working with sequence, series, or a series of partial sums. So we're given an infinite series here. An infinite series always refers to a partial sum, but instead of just a partial sum, this is going toward infinity, so it's the actual sum of the terms of a sequence. Now it says complete parts A through C below, so I will kind of clue you in what parts A through C are. So here what we're going to do for part A is we're going to find the first four partial sums. So we're going to look at S sub 1. Now clearly we start with n equal 1 here, or k equal 1. So this is going to equal 1 over 4 times 1 minus 2 times 4 times 1 plus 2. And as usual, I'm going to just go ahead and write all of these out first. So this would be 4 times 2 minus 2 times 4 times 2 plus 2. S sub 3, I have a, whoops, these are a 4 on top. Got to make sure these are 4s on top. Whoops, I've got a green one, 4, and then this would be a 4. And that 4 comes from what was given to us. So S sub 3 then would be 4 times 3 minus 2 times 4 times 3 plus 2. And then our last one, S sub 4, would be a 4 on top. 4 times 4 minus 2 times 4 times 4 plus 2. So now I can see my pattern here. I have the 4's fixed, it's not changing. The 4 is fixed in the denominator, the only that's changing is the 1, 2, 3, 4, 1, 2, 3, 4. So again, I always do that just because a lot of times I'll lose track of what I'm trying to be doing, and I will start substituting in numbers that I shouldn't. Okay, so we have 4 over 4 times 1 is 4, 4 minus 2 is 2, 4 times 1 is 4, 4 plus 2 is 6. So I get 4 over 12 here, which is 1/3. So S of 1 equals 1/3. Okay, next we have 4 on top. 4 times 2 is 8, 8 minus 2 is 6. 4 times 2 is 8, 8 plus 2 is 10. So I have 4 over 60, which reduces to 2 over 30, which is going to reduce to 1 over 15. You know, actually I think I'm going to do this difference, because what I'm doing here is I'm finding I'm not finding the partial sums here. I'm finding the a's here. I'm finding the terms of the sequence. So I need to write this differently. This would be a sub 1, a sub 2, a sub 3, a sub 4. So I'm finding the terms of the sequence here, and then next we'll find the partial sums by adding them. So again, this was 4 over 60. I'm going to make sure this is an a here. It's a term of the sequence, it's not a sum. So 4 over 60 would be 2 over 30, which reduced to 1 over 15. So a sub 2 is 1 over 15. Okay, so again, these are the terms of the sequence. They're not the partial sums yet. So here, again, I see a lot of patterns here. 2 goes to 6, 6 goes to 10, so I'm basically adding 4 here. We'll see if that holds. 4 times 3 is 12, 12 minus 2 is 10. Yep, that held. I still added another 4. 4 times 3 is 12, 12 plus 2 is 14. So that's true as well. So you can see the patterns repeating themselves. So here I could do my cancellation first if I wanted. 4 and 10 would reduce to 2 and 5, and then the 2 would cancel into the 14. I'm just going to go ahead and write this out. So 4 over 140 would reduce to 2 over 70, which would be 1 over 35. So a sub 3 would equal 1 over 35. Okay, let's look at our last one here before we find our partial sums. So again, the 4 is fixed. 4 times 4 is 16. 16 minus 2 is 14. 4 times 4 is 16 plus 2 is 18. Okay, so again, I could reduce first if I wanted. I'm just going to go ahead and multiply it out first and then reduce. That would be 252. And if I reduce that, 4 over 252 would be 2 over 126, which reduced to 1 over 63. So this would be a sub 4 equals 1 over 63. Now I can find the first 4 partial sums. I had to find the terms of the sequence first. So let's go ahead and look at the partial sums. So S sub 1 would equal a sub 1, which is 1/3. So S sub 1 is 1/3. Okay, next I'm going to find the second partial sum, which would be a sub 1 plus a sub 2, which would be 1/3 plus 1/3 from here, plus 1 over 15. Okay, and I'm just going to write all these out, and then I'll go back and add them up. So S sub 3 is a sub 1 plus a sub 2 plus a sub 3, which would be 1/3 plus 1/15 plus 1/35. That comes from right here. And then our last partial sum that we're going to find is the fourth partial sum. 1/3 plus 1/15 plus 1/35 plus 1 over 63. Okay, so let's go back up and start finding these sums. So this partial sum, 5 times 3 would be 15, so this would be 6 over 15, which we reduce, each are divisible by 3 to 2/5. So S sub 2 would equal 2/5. Okay, so for our next one, I'd have 1/3 plus 1/15 plus 1/35, but remember, I already know that this partial sum I just found above was equal to 2/5. So sometimes that's easier to take 2/5 plus 1/35 than adding the 3 fractions. So a common denominator here would be 35 between 2/5 and 1 over 35. Multiply top and bottom by 7 here. 7 times 2 is 14 plus 1 is 15 over 35. Both of these are divisible by 5, so I'd end up with 3 over 7. So S sub 3 equals 3 over 7. Okay, we're going to use that same shortcut again. We already know the sum of these first three from up above was 3/7. So the common denominator between 7 and 63 would be 63. I have to multiply top and bottom by 9 here. 9 times 3 is 27. 9 times 7 is 63, so I end up with 27 plus 1 over 63, which is 28 over 63, which are divisible by 7. So 7 times 4 is 28, 7 times 9 is 63. So the fourth partial sum is 4/9. Okay, so now what we have here then is S sub n. I'm going to write these out so I can hopefully start to see a pattern. 1/3, 2/5, 3/7, 4/9. Of course, this would continue on forever, but I'm only looking at the first four to help me find my pattern. Well, I definitely do see a pattern here. So I'm noticing that the numerator is increasing by 1 each time. So 1, 2, 3, 4, etc. And then the denominator is interesting. It's a sequence of odd numbers. 3, 5, 7, 9. I could do 11, 13, 15, 17, etc. So I did part A. I found the 4 partial sums. So for part B, what I want to do is I want to find the formula that describes this using the recursive part of the formula. Okay, let me see if I can save that. Get the pen to work. And I think on this one we won't use recursion. It's not asking us to, it just asks us to find the formula. So it's asking us to find S sub n in general. Well, I know I'm going to start with n equal 1, 2, 3, 4, 5. So it's pretty clear to me that my numerator is just going to be n. Now the denominator is going to be this sequence of odd numbers. So I need, how do I create a sequence of odd numbers? Well, you take any number and double it, and that will become even. And then you could either add or subtract 1 to come up with an odd number. So in this case, that's going to be 2n plus 1, because if I plug in a 1, 2 times 1 is 2, 2 plus 1 is 3, and that's what I need to start with here. Now if I wanted to start with a 1, I would have subtracted 1. Okay, so this is my sequence here. Now what I want to do then is I want to find the next 5 terms of the sequence it's asking me. So I'm going to come up here and do that. So I have 1, 2, 3, we'll just do the next 4. Okay, well, I'm pretty clear that this is going to be 5, 6, 7, and 8. And then my denominators are going to be the sequence of odd numbers. So 3, 5, 7, 9, 11, 13, 15, 17. So those are my next 4 terms of my partial sums. Now, I'm trying to figure out what's going on here for part C. They want me to make some sort of a conjecture about the value of the series, meaning if I were to continue to add these up, what would these be going toward? So 8 over 17, that would be going to 9 over 19, and then it would go to 10 over 21. This is getting really, really close to 1/2. So if it was diverging, it might be going toward infinity, but it seems to be getting closer and closer and closer to 1/2. So I think that this is the sum, k equal 1 to infinity. I don't even know if I remember my original problem. 4 over 4k minus 2, 4k plus 2. Is equal to 1/2. And again, if I kept writing these out, I could see these decimals. This would be 0.3 repeating, 0.4, 0.3 divided by 7. I have to check that one. 0.42857. You'd look at all these fractions. 4/9 is getting very, very close to 1/2. You'd see all these decimals getting closer and closer to 1/2. So it is converging to 1/2, and that's giving me the value of the infinite series. So that was a pretty interesting one. Okay, last one we're going to do. I'd like to do a couple more, but the lecture's getting a little bit long, but these problems are fun. So let's go ahead and look at this last one. So we have, suppose a ball is thrown upward to a height of h naught. So h naught means the initial height. Each time the ball bounces, it rebounds to a fraction r, in this case 1/2, 0.5 of its previous height. Let h sub n be the height after the nth bounce, and s sub n would be the total distance the ball has traveled at the moment of the nth bounce. And complete parts A and B below, and I'll fill out what A and B is. But first, before we get started, let's go ahead and look at what this looks like graphically so we can kind of get an idea what's going on here. So we're going to call this our start, and we're going to throw it up because it says it's thrown upward to a height of h naught. So this is h naught right here. And then what it does is it comes down and it hits and it bounces. So this is at time 1, if we want to think about it like that. This is the first bounce. And then what it does is it bounces up, in this case, half the height, 0.5. And so this height right here is h1. So this is h1. And then it's going to hit again on the second bounce, and it's going to go half the height, and this is h2. This would be h2 would come straight across right here. And then this third bounce would be half the height, and this would be h3. And this would come over here and be h3. So you can see kind of what's going on here. It would be half the height, be h4, etc. So this is a kind of a fun problem. So what we have here then is h naught, h1, h2, h3, h4. Those are the terms of the sequence. The partial sum will be the total distance traveled by the ball. So let's go ahead and start kind of trying to build this up. Let's try and find a sub 1. So in this particular case, a sub 1 would be, actually we better start with a naught, I suppose. A naught would be our height that we threw it up to. So I'm going to use h just to be consistent with our picture here. So I'm going to go h naught equals, our initial height was 15. So h1 would be the height after the first bounce, or at the first bounce I should say. So that would be half the height of the 15. So it would be 15 times 0.5, which would be 7.5. And then h2 would be half of the 7.5, which would be 7.5 times 0.5, which would be 37.5. That doesn't seem right. That would be 7.5 times, 0.5, forgot the decimal, so it would be 3.75. And then h3 would be 3.75 times 0.5, and that would be 1.875. And so you kind of get the idea here of what's going on. It would be half the height, so the 0.5. Now you could have a problem where you're not given 0.5, you might be given 0.4 or 0.8, so you have to look at the value that you're given. So here I'd have half of 1.875, and I'd have 0.9375. Okay, so I could keep going on and on, but this is enough to get started. Now this one's pretty neat. We're going to have to think a little bit harder. We can't just kind of arbitrarily walk into this and start adding these together, because we're given some very specific definitions. So S sub n, we'll start with S sub 1 here, would be the total distance traveled. Okay, so we're looking at the total distance traveled at the moment of the nth bounce. So this would be total distance traveled at the first bounce. So that means we have to kind of follow our picture to see what's going on here. So if I follow this, I'd have our height was 15. So I'd have 15 throwing upward and then another 15 coming down when it hits. So S of 1 would equal 15 plus 15, or 30. So S sub 1 is equal to 30. Okay, now let's find S sub 2. So S sub 2 would be 30, because I've already traveled 30, and then I'd have to have the height of the next bounce, and then coming down and then hitting. So H sub 1 was 7.5. But I can't just add 7.5, I have to add the plus 7.5 going up and the plus 7.5 going down. So this is plus 2 times 7.5. So 30 plus 15 is 45. So here I'd get S sub 2 equals 45. So S sub 3 would be 45 plus 2 times, because I have to go 2 times because I'm going up and then down the same distance, 2 times 3.75. So I'd have 45 plus 2 times 3.75. So this would be 52.5. So S sub 3 is equal to 52.5. S sub 4 then would be the 52.5 plus 2 times the height of the next one, which would be 1.875. Remember, that's doubled. So I'd have 52.5 plus 2 times 1.875, which is 56.25. Okay, so S sub 1 is 30, S sub 2 is 45, S sub 3 is 52.5, and S sub 4 is 56.25. So that's what we've come up with our partial sums. Now, always look at the directions to see if they want fractions for these partial sums or if they want you to have decimals and then follow the decimal instructions for rounding. So as we're working through here, the next part would be to make a table of 20 terms of the sequence. So I think Excel would be kind of a good idea to do that. We definitely see a pattern here. You don't want to write these out by hand. But what we want to do is to try and figure out what's going on as we get higher and higher terms. Is this going toward a particular value? And it has to be, because if you think about it, as this ball bounces, it's going to stop bouncing. I guess if you want to think about it going on forever, pretty soon it's bouncing so little, it's just kind of barely going here. But the total distance traveled will go toward a particular value. So let's see how we can work with this in a spreadsheet to make things a little bit easier. You could also try and write this out in terms of function like we were doing for the previous problems, and then possibly graphing it on your calculator and trying to come up with a limit that way. Okay, so I opened up Excel and I kind of titled some things here that I thought were important. We want the number of bounces. So as we start with our number of bounces, we have to remember that 0, when I threw the ball up in the air, is kind of what we have there. So I'd start with 0, and of course 1, 2, 3. We wanted to go up to 20. I don't want to type out 20 here, so I'm going to use my fill handle and fill this up to 20. Now again, this is giving me the number of bounces. So this is 0 bounces, and the height after 0 bounces, for our problem that was given, it was 15. So that is what was given. Okay, now the total distance traveled after the nth bounce is something we can fill out next, but I want to do the height after the nth bounce. After it bounces once, it's half as high. So I can write a formula for this so I don't have to do all this by hand. So that is equal to the previous bounce times 0.5. Okay, so now I have a height of 7.5, and then again I'll use my fill handle to fill in these formulas. Now I can see quite a bit of information going on here. I want to see if I can format this a little bit different. Let's do number. I just want to be able to see more decimal places. I don't want to see the scientific notation. So I can see that the height is getting lower and lower and lower, and here it's hardly bouncing at all because it's always half as high. So technically it could go on and bouncing half as high forever, but because of the diameter of the ball, obviously at some point it can't bounce any higher if it only goes half as high. And then we have the total distance traveled. Okay, so the total distance traveled, I want to write another formula for. That is equal to, in this case, let's see if I can pop this open. Remember, that was 15 plus 15. That's this 30 right here that I should be getting. So that's equal to 2 times, and then I want to go ahead and just use my formula to write that. Now, the next total distance traveled, let's go ahead and look at our notes here, is going to be the previous bounce plus 2 times the current height. Okay, so this is going to equal the previous bounce, which is here, plus 2 times the current height, which is 7.5. But again, I want to use my absolute and relative cell references because I don't want to have to type all these numbers in. So I should be able to copy this formula all the way down. And as I look here, I can see the total distance traveled as my ball bounces is getting closer and closer to 60. So that's the information that doing this on a spreadsheet very quickly can help us figure out. So I'm going to go ahead and pop this into our lecture and look at all the neat things that we see here. So first of all, I have my partial sums. I have the 30, 45, 52.5, so 30, 45, 52.5, 56.25. So I could keep going on and on forever doing this by hand, but the spreadsheet and using our formulas is really helping us write this. And we can see that this, if we kind of match it up with here, S sub 1, this is the first partial sum, this is the second, third, fourth, etc. And so as I move on down here, this is going to be, what did I do, not copy all this in? Let me pop open here. Might not have brought all my partial sums across. Oh yeah, so here I am at cell 20 or row 20, so I'm good. I can see that this is approaching 59.999885556. So that tells me the total distance traveled is approaching the arrow means approaching 60. I don't know if we were using inches or kilometers. I think we were using meters. So that's what this information is telling me. So it's always fun to use a spreadsheet, so I'm glad we got to use a spreadsheet here. This lecture did get pretty long, but hopefully I did a lot of examples that will help you be able to work through the homework problems without any troubles. As usual, if you have any questions, please let me know. I'm always happy to help.